Hey folks, Todd Coburn here with your Aerospace Structures series. This video is part of our Statics series. We're working on rigid bodies and vector products. And I realized in video 5C, I left folks a little bit hanging on how to handle the hardest problem of the lecture that kind of ties everything together. I think I commented bang, bang, pop. Do it like this, bang, bang, pop, rather than showing how it's done. Actually, that problem is more straightforward than it appears, but it's one of the trickier problems, so it actually needs described in more detail. I was in a bit of a hurry trying to get the video out before, so I'm going to remedy that now. So stand by and we will walk through that problem together, bringing these concepts of vector products, taking the dot product and the cross product and understanding how those work and how we can project vectors and use this to find distance between vectors. So here's how it works. So we are working on this problem, and this problem has a cube just as a three-space visualization thing to work our methods on, and we're going to find out we have this force applied P. And we're looking for four different things, going from pretty straightforward to a little more tricky as we ask for what is the moment of this force about point A, what is the moment of this force about the edge AB, what is the moment about the diagonal AG, and then the trickiest one, how do we find the perpendicular distance between AG and FC? So let's walk through these step by step rather than bang, bang, pop. Here's how it works. Okay, so this is, once again, this problem is out of Beer and Johnson, a great text for this kind of stuff. Beer and Johnson's problems tend to be a little bit tricky, but it's a pretty foundational text. It's the same text that I used back in one of the early editions when I was in school. So our first problem is pretty straightforward. It's asking for what is the moment of this force P about point A. Okay, that's one of the more straightforward problems to ask. And because now normally when we're calculating moments in industry, we'll just take the perpendicular distance times the force and calculate the moment. The whole idea that we're covering here in this lecture, in this subpart of statics, is what about when it's more complicated than that? What about when it's not easy to figure out what that perpendicular distance is? In that case, we're going to take a cross product. And if we follow our method, it's pretty straightforward. What we need to do to get the moment about A is take a line segment from point A to any point along the vector F. If we take a look at the vector F, we see that the vector F goes from here to here. We're looking for the moment about point A, which means we can take a line segment from point A to any point along F. We can use this. This goes from A to a point along F, right? That force F goes in this line of action, and we can actually use any line. We could use this line to that vector. We could use the line vector here. We could use this line to this point or out to any other point. Any of these position vectors we can use, and we can say, what is the R cross F? The position vector crossed with that force will give us the moment about point A. Since R goes from A to any point along that force P, that crossed with the force P will give us the moment about A. So let's walk systematically through how we will solve each of these. We're going to start off by solving for the moment of P about point A. This is pretty straightforward. We're going to need to use the cross product of R cross F. Now the question is, what R do we need and what F do we need? So let's start out by saying, well, if we want the moment about this point A, all we need is the line segment from A to any point along the vector P. We can use this. This line segment is AF. Okay? We're also going to need the vector p as a vector. So let's start off by getting these two things. Well, if we want that line segment AF, we can look at this moving from A toward F. We're going to move at a positive A units in the x direction, so positive AI, and we're going to then move from there a negative A units in the j direction, and we're not going to move any direction in the k. So that is our vector AF. Okay? All right. Now we're going to need our vector P. We know the magnitude of P is P, but we don't know what the vector is. So first we need the unit vector of the line segment going from the line of action of P goes from F towards point C. So let's go ahead and just calculate AC for a minute. Well, if we work from, not AC, FC. If we start at F and we move towards C, we're going to have to go in 0 in the I direction. We're going to move plus A in the Y direction, or the J direction, and then minus A in the K direction, which means the vector FC is AJ minus AK. Okay? Now that is FC. What we're going to need to do to get that force unit, the force vector, is turn this FC into a unit vector. We want the unit vector along FC. Okay? That means we're going to need the magnitude. That will be FC divided by the magnitude of FC. Okay? Now, so let's take a sidebar and let's calculate the magnitude of FC. That is just the square root of a squared plus a squared, which is 2a squared, which is just square root of 2a, or a squared of 2. So then when we get the unit vector, we find we're just taking this guy. This is just a over square root of 2a minus a over square root of 2ak. This is j, which is equal to just 1 over the square root of 2j minus k. Okay? Now to turn that unit, the force now will be the magnitude of the force times the unit vector of its line of action, which means we just take this mother and multiply by p. Therefore, that is just p over square root of 2j minus k. Okay? So we've calculated AF, and you'll notice that that is right up here. And we've calculated P, and you'll notice that that's right here. So looking at those two things, we're now going to erase the ink on the slide and work from there. Since we found this vector AF, we're calling this AF. From A to F, we're calling it that vector, and there the book is calling it the position vector R to F from A. That's that nomenclature, and we found it to be this value. We also found that vector force by taking the unit vector, lambda FC, and multiplying by that magnitude of the force. We found that to be this. Since we have now this vector, R cross F equals M. So we have R is just our AF vector, and we're crossing it with our P, which is our P vector. That's this one and this one. Okay? When we take that cross product, that's what's done right here. And you can actually lay out your determinant or solve this component by component where we have, let's go ahead and do that. M about A is simply going to be our position vector AI minus AJ crossed with our force vector, which is P over square root of 2J minus P over square root of 2K. Now we can actually form our determinant to do this, or we can just do it step by step, where we take, that means we have PA over square root of 2, and then we have I cross J. We've got, then we've got minus AP over square root of 2, I cross, this is plus I cross minus K. Okay, this was I cross J, yes. I cross minus K, yes, okay. And then we have our next term, which is, let's just say it's plus AP over square root of 2. And now we have minus J crossed with plus J. And then our last term is going to be AP over square root of 2. And we're going to have minus J crossed with minus K. Okay, if we look at this, we see, okay, let's move it back here a little bit. This is just PA over PA over square root of 2. That's in every term, multiplied by I cross J. So if we go from I cross J, that's going to give us positive K. That's going to be K. Then we're going to take our next one is I cross K, which is going to be negative J, and we have a negative sign out here, so it's going to be positive J. Then we're going to have negative J crossed with J, and that's going to give us a 0. And then we're going to have minus J crossed with minus K. Minus J minus K, which is going to give us positive I plus I. Which means we're going to have PA over square root of 2, and our components are going to be I plus J plus K. And if we look up here, AP over square root of I plus J plus K, that's what we got. Now you could also have laid out the determinant, taking your position vector, A, 0 for the I, J, K, and your other vector, which is P over square root of 2. Oh, excuse me, there's a 0 here. This is P over square root of 2, and this is minus P over square root of 2. Let's see, oh, and this was a minus also for our position vector. We could have formed this determinant and solved that to get through this cross product, if you prefer that method, which is actually better for more complicated problems. So we just validated our cross product. So let's rethink what we did here. What we did here, we said, all right, we're going to need to take the cross product of this position vector crossed with this force. So we started off by getting our position vector AF. Okay, that's the position vector from the point we want the moment about to any point along the vector. We then calculated the unit vector FC, which means we calculated FC itself. Then we calculated the magnitude of FC. Then we used that to get the unit vector FC, which is just FC divided by its magnitude. Then our next step, this is 1, 2, 3, 4. Then our next step was to get the position vector P, or the vector P, which is just P times the unit vector of its line of action. Then to get the moment, we then said the moment at A is simply any position vector from A to that force, AF, crossed with, and the book is calling it this, crossed with our vector force P. And then we solve that cross product, which is done right here, which gives us our answer. Okay, let's try this another way. Remember I said we can take the cross product of any line segment from the point to the vector, cross with that vector force to get the moment about A. That means let's try a different point. We find, if we look at our diagram here, another convenient vector that goes from A to the vector, the line of action of P goes right through this point C. We could have also used this vector. This is AC. AC is simply, we move in the positive I direction, A units, and then we move in the negative Z direction, A units. Okay? So actually we could also have calculated this moment about A as the vector AC, that position vector, crossed with our force P. That is, AC we said is A times I minus K, crossed with the magnitude of our P was P over square root of 2, and we have this J minus K vector. That means when we do this, we're going to get the scalar PA over square root of 2, and then we're going to have I crossed with J plus I crossed with negative K plus, then we're going to have negative K crossed with J, and then plus negative K crossed with negative K. Okay? Now when we do that, we look at our little, it's convenient to say, wait a minute, this is I, this is J, this is K. So if we take I cross J, that's going to give us a positive K. So we have this P over A over square root of 2. This is going to just be a K, positive K. Then we have this next term, which was I cross with J. Let's see, I cross with J, then I cross with negative K. This term is I cross with negative K. So we got I cross with negative K. That's going I cross with negative K, which is a positive J, plus J. Our next term here, we've got a negative K crossed with a positive J, and that's going to be an I. And then this last term, K crossed with K is 0. So actually we find out that this moment is the same as we did before. The first time we use this AF cross with P, since that is a line segment going from the point we want the moment about to any point along the vector. And then we took a line from the same origin, because that's what we want the moment about, to any other point. We use this point C, and we got the exact same moment. So we can use this cross product by taking any convenient line segment, crossing that with the force vector. That's how this works. Okay? So let's go ahead and let's move to our second example. So before you move to the second example, you need to do this over and over again, getting the moment of that force P about A until you can do it like this. Okay? All right. Once you've done that, you're ready to move to our next example. In this next example, what we're going to do is we're going to calculate the moment of P about this line segment AB. Okay, the same process. Now since we want the moment of P about AB, all we have to do, so what that means is we're going to get the projection of the moment that P causes with AB. So to solve this, what we're going to do is have to look at this and say, okay, we're focused on getting the projection around this line segment AB. Now this force P is causing a moment about AB. And what we need to do is first calculate what is the moment of P about any point along this line of action AB. The convenient points we can see is we can get the moment about A, or we can use the moment about point B. Since we already have the moment about point A, we'll use that. This R cross P caused a moment going out like this. This is our M about A, perpendicular to those two. So now since we already have that moment at some point along the line of action of AB, we can just take the dot product of the unit vector AB, with that moment from any point along the vector, which was MA. Okay? Now the unit vector AB, what we do is take the length of AB divided by, or the vector AB divided by its length, which we can see by inspection, that is just I. This unit vector lambda AB is simply I. So actually, if we did I say cross? We're going to take dot, right? Once we have this moment moment at any point, MA, we can just take this dot product, I dotted with that moment, and that will give us the projection of the moment upon that unit vector. Remember, we can't use this line segment AB crossed or dotted with because that will give us too big of a number. We need the unit vector along AB, which is simply I. So we take I, which is the unit vector along where we want to know the component about, dotted with that moment, which was here. That gives us the perpendicular component. We're going to find the component of that moment A along that. Taking the dot product, we see that's going to be I dotted with this stuff. That's going to say, okay, we've got this magnitude, and then we're going to have I dotted with I is the only term that's left. These other terms are going to be 0, which means just AP over square root of 2. Got that? I dotted with I is simply 1. Remember that? Okay. So that's how we solve this. Okay, now that we have solved for the moment about AB, the moment of force P about AB, and we use the moment of P about point A, right? This force P crosses a moment about point A that looks something like this. This is the moment of P about A. That's what we used in part A, and that's what we used in part B. We then took the projection by taking the dot product of the unit vector I, and that gave us this projection. This was the projection of M1AB, this little component. That's what we just got. Now another way to do this, we could have said, well, actually this P also causes a moment about B. It caused a moment out something like this. That's not in the same direction as B, but it's some wacky moment like this. Actually, let me draw it out more like this. This is the moment about B. We could have used this. If we had this moment, we could have then taken the dot product of I with that moment. So before moving on, if you really want to understand this material, here's what I recommend. Let me back up. I'm going to recommend that you do this. Calculate the moment about B. And then take the dot product of lambda AB dotted with the moment about B. To get that MB, what we're going to do is you're going to need to get BF. You're then going to, that's your first step. Then you're going to calculate the moment of P about B, and that's going to be BF crossed with the vector P, right? We already have the vector P right here, and you're going to calculate what BF is. You can now calculate that moment. Then you can calculate 3, the vector. Now that you have this, you can now take the dot product of lambda AB, which is still just I, dotted with the moment about B, and you will get the same projection of P about, that's actually the moment of P about AB. Okay, I recommend you try that, and you should be able to match the exact same answer that we saw in part A, which was right here. Once you've done that, you've got it, and you're ready to move to the next part, part C. Now for part C, they're looking for the moment of P about the diagonal AG. So what we're going to do here is we're going to need to first calculate the moment of P about any point along AG. So if we look at AG, that means we can use the moment of P about A, or we can use the moment of P about G. We already have the moment of P about A, so we might as well use that. Okay? Then, since we want the component along that diagonal, we'll need to calculate what the unit vector is in the direction of AG. In order to do that, we're going to take AG, which is simply moving from A to G. We're going to go A in the I, right? And then we're going to move negative A in the J, and then we're going to move minus A in the K, right? That's our AG. We then calculate the length of AG. We take the unit vector of AG, which is this over this. And then we're going to take the dot product of that lambda with M. That's what's shown here. Here they're calculating one big step. They're calculating that unit vector along AG, or the way they call it is G from point A. They're taking the moment we calculated before, and they're taking that dot product, and that gives that magnitude of that force P along that line of axis AG. Now, since if you just kind of want a loose understanding, you can move on. If you actually want to really understand this, I recommend try something else. You can now calculate the moment. Calculate the moment of P about G, which means we're going to say, all right, we can take any line segment. We want this about G now. So we can use, okay, if we want the moment about here, we can use this position vector, which means GF crossed with P is going to give us the moment of P about point G. Then we can use that moment, take the dot product of the unit vector AG, which we just calculated, crossed with this new moment, and you should get the exact same projection. If that works, you're ready to move on. If it doesn't work, you're going to need to try it again. Got it? Okay, now that we've understand those three principles, let's go on and try the last one. And this looks like the hardest one, at least at first. Okay, for the last problem, we're looking for the perpendicular distance between AG and FC. The perpendicular distance between this line here and this line here. Now, in order to solve this, we're going to use the principle. Remember, if we have the moment, remember R cross F is equal to a moment. And the magnitude of the moment is equal to the force times the perpendicular distance. Therefore, if we have a moment and we divide it by the moment of this force about this axis. So if we have this vector, the moment about this line of action, remember we calculated the last one, we calculated MAG. MAG is the moment of P about this line AG. So that is the projection of the moment along that line of action. Since we have the moment along that line of action, we can say, okay, if we wanted to know R, any position vector, the perpendicular times the force P is equal to the moment about that axis, right? We're using this thing. This is the R cross F, but what we're using is the R is the perpendicular distance, which breaks it down to just the scalar. Perpendicular distance times force equals moment. Then we're going to solve for that perpendicular distance is the moment divided by the force. We already had the moment along this line of action AG. We used it by calculating, in the last section we did that where we calculated that MAG, and we found it to be equal, if we look back, this was the moment about AG we just calculated, right? So we actually can just take that moment, which is AP over 6, M this is over D is equal to this perpendicular, over P. This is AP over 6, square root of 6, divided by the magnitude of P, just leaves us with A over square root of 6. So using that principle, that since we already have the moment that R cross F equals M, and actually if this distance is perpendicular, since it's also equal to the RF sine theta, and that R sine theta is just a perpendicular distance, which means just DF equals M, solving this, D equals M over F, and that's what we're doing here. The one extra thing that the book does is it first checks to make sure the dot product of those two is 0, and that shows that these two are perpendicular. Remember, if they're not perpendicular, the dot product will leave a component. If the dot product gives 0 component, that means they're perpendicular, and that's what this check is doing here. So there is a little more detail on that particular problem. Actually, this is a really good problem because that little cube and working those moments, projections, and the perpendicular distances is very insightful for being able to solve statics problems for forces and moments when we have more complicated vectors involved. I recommend highly that you stay in this lecture and practice. And if you need more practice other than this example, once you've solved this example a bunch of times, if you actually still don't feel like you've got it, get your Beer-Johnson or a Hibbler, pull up this section, and work through some of the other example problems in the text. Subscribe if you haven't already. I will try and add more problems in the future that are worked so you can drive this principle home further. If you really get this principle, you're gonna find that a lot of the stuff we're gonna do after this gets a lot easier. Make sense? Enjoy.